Identifying independently moving objects is an essential task for dynamic scene understanding. However, traditional cameras used in dynamic scenes may suffer from motion blur or exposure artifacts due to their sampling principle. By contrast, event-based cameras are novel bio-inspired sensors that offer advantages to overcome such limitations. They report pixel-wise intensity change asynchronously, which enables them to acquire visual information at exactly the same rate as the scene dynamics. This working principle offers potential advantages such as low latency, high temporal resolution, high dynamic range, and low power consumption. Given as input the data acquired with an event camera, the goal of this work is to develop a method that can identify independently moving objects. Considering the clustering nature of the problem, our method is built on top of a classical energy-based multimodal fitting scheme. Specifically, we define a spatial-temporal graph through the events and formulate the problem using Markov random fields with motion model fitting. To build the spatial-temporal graph inside the space-time volume, we compute the Denali triangulation on the active pixels. The resulting 2D graph is used to make a simple connection principle, according to which the 3D spatial-temporal graph is established. Our energy function describes a standard Markov random field problem plus an additional regularization term. The data term pursues locally optimal alignment for each event. As a contribution, we've reformulated the original motion compensation scheme such that the energy is minimized instead of being maximized, and overall fitting cost can be given by the sum of unary terms. To encourage spatial coherence inside a cluster of events, a pulse model is simply used. Besides, we introduce a minimum discrete length principle, which tries to remove unnecessary redundancy in the model pool, making it possible to converge to the actual number of independently moving objects. To solve the discrete continuous optimization problem, we employ a block coordinate descent strategy to optimize labeling and motion model fitting in an alternating manner. To initialize, we carried out a multi-level subdivision operation on the given spatial-temporal volume of events. By fitting these subvolumes to the motion compensation scheme, we get a number of motion model candidates. This strategy aims at capturing moving objects of different size. For example, the blue dashed subvolume captures a box in the background, which leads to an image of warped events with high contrast at the background structures, whereas the green dashed subvolume captures part of a smaller moving object, leading to high contrast around it. Consequently, a redundant set of motion models is obtained and used by the optimization. Our method shows state-of-the-art performance on datasets accompanying recent publications. We used evaluation metrics such as detection rate and intersection over union. Compared to an existing method based on morphological operations via empirical thresholding, our method leads to more accurate segmentation on the boundary of objects. The data used also consists of outdoor environments, such as a traffic scene. Compared to a two-step exploitation and maximization method, our energy function leads to better results in terms of local smoothness and global consistency. Besides, we also perform a number of qualitative experiments showing the versatility of the proposed method. We released the software and our data to foster future research on event-based motion segmentation. Thanks for watching.